So what is the distinction between aerobic and anaerobic? In case of anaerobic, we never use what is called environment to decompose the microorganisms. So here, in absence of air, everything is happening. But in case of aerobic, conversions are happening in presence of air. So in a nutshell, this biogas plant looks something like this. So it will be having one inlet tank and one fermentation chamber and one outlet tank. Okay. So here, what we do, we feed material, and there's a pipeline which is connected, and it is injected through this pipeline. And then this microorganisms activity will be carried out inside the fermentation, and then this slurry is come out, and then that can be stored, and we can increase the quality of the fertilizer by applying some kind of methodology called vermicomposting, and we can get a enriched quality of fertilizer which is organic. So here we are mixing say feedstock plus water. Okay, so this is very, very important, and what proportion we are making in order to have appropriate total solid content. So we'll see what are the feed materials we can use. So as far as feedstocks are concerned, we can use kettle dung as feedstock. Then vegetable waste we can make, or we can feed it in the digester, and co-digestion is possible. Then sometimes we can use some kind of additives like orange peels, newspaper, tea waste. Appropriate additives to be selected for appropriate feedstocks. So that way we can maximize the biogas production. Okay. So here what I am talking about is the feedstock. These many feedstocks can be used. There are innumerable numbers of feedstocks we can use as feed material for biogas plant. So that will be decided based on the characterization. So we can do the characterization first before feeding to the biogas plant. And what this fermentation chamber is giving, so we can have microbial activity, and we have to concern some important aspects like hydraulic retention time, which defines something like the volume of the digester. This is the fermentation chamber, to the volume of the feedstock what we make daily. Okay, so that's why what we'll get, it will be in terms of days. Okay, so in very winter season, what I mean to say, when the climate is very, very cold, then under that condition HRT will be longer. Okay, because it takes longer period of time to digest all the nutrients present in the feedstock. Okay, so for our climate, like in Arunachal Pradesh and mostly in northeastern part of India, so 55 days to 60 are perfect timing for almost all the conversion actually takes place during that timing. And what we'll get from these digesters, we'll get heat, okay, which can be used for cooking, okay, that gas, cooking gas, and we can use that gas by providing some kind of what is called filter or cleaning devices. We can generate electricity by using this engine generator route. Okay, so that's how we can utilize many of the things. Like we can use gas for cooking, we can use gas for electricity generation, and we can use the slurry for fertilizer. And of course, we can enhance the quality of the fertilizer by doing vermicomposting, right? So there is a challenge for purification of biogas. So once we purify it, as you know, GAIL, Gas Authority of India, is thinking in a big way for pipeline for natural gas distribution. So if you have this kind of plant, and if you have a very good purification system, then you can feed this methane into the pipeline of natural gas. So that way you can gain out of it. Something like our net metering system, what is used in solar photovoltaic system nowadays. So you can generate your energy and you can feed it to the grid, and you can gain energy, okay, when you are not utilizing the generated energy in your household, and you can get it back when you require energy. Okay, so net metering system will be responsible for calculating the amount of energy which might be gaining, or maybe sometimes you have to pay from your pocket sometimes if you are utilizing more from the grid. This is something like that. So biogas, already you know, it's a combustible mixture of constituents, mainly of methane and carbon dioxide, and it produced through the decomposition of organic matter by the anaerobic bacterial in absence of oxygen, and composition of this biogas depends on the feedstock. Okay, the kind of feedstock you use. And also we must know something about impact of methane on climate. Okay, so methane is a major greenhouse gas, okay, which is about 22 times dangerous than carbon dioxide. So we can calculate it mathematically how dangerous this methane is. So you also know that about the Mars gas. Okay, this is nothing but methane gas only. So methane contributes about 20% of the greenhouse gases. So this information also we must know. So these are our challenges, how this gas can be utilized effectively for power generation, okay, to reduce this global climate impact. Just for your information, like biogas installation capacity in India, how it is progressing, you can see this plot. So it is progressing, okay. So here in 2019, it's about 16 megawatt biogas plant has been installed in India. And if we compare with the world scenario, it's about 20 gigawatt, okay, 20,000 megawatt of energy which is installed globally. So what are the advantages of anaerobic digestion? So this anaerobic digestion of waste material is used to produce renewable energy. It produces fuel and fertilizer with better quality. Energy security is also one of the concerns. That is, energy requirements of some industries. Maybe a dairy farm can be fulfilled through anaerobic digestion of waste generated within the industry. The digesters can be used for stabilizing the sewage of rural communities by reducing the incidence of disease caused by parasites and pathogens, right? So that is taken care by the anaerobic digestion technology. It reduces greenhouse effect because we are using it for power generation. Then intensity of the greenhouse potential decreases significantly. It reduces landfills. Okay. Now come to the feedstock again. So now we'll quantify the potential of this feedstock and then how much energy can be generated by using those different kinds of feedstocks. So feedstocks may be kettle down, vegetable waste, kitchen waste, organic matter collected from municipal solid waste, then lignocellulosic biomasses. So you can see the availability of raw material and gas yield here in this chart. So here you can see cow dung. So production time is 10 to 15 kg per day per head. And then, so this is production rate, and gas yield is about 0.34 cubic meter per kg of dry matter. Okay, and in case of poultry manure, it's about 0.06 kg per day per head. Okay, one poultry can give about 0.06 kg, and then gas yield potential is about 0.4 to 0.56 cubic meter per kg of dry matter. And then you can see the sheep manure, and then we'll have nitrile and rice husk. It's significant, you see. So it's about 1.1 to 1.13 tons per hectare per year, and its potential is about 5.67 cubic meter per kg of dry matter. Okay. So algae also we have, then water hyacinth you can see. So these are the potentials of biogas. Okay. So how much biogas we can generate from per kg of dry matter, right? So we can use those biomasses as a feedstock for energy generation in anaerobic digester. So what are different models of biogas digesters are available? We'll have fixed dome and then floating drum type biogas plant. Okay. So under fixed dome type, we'll have Dinmontu model, Janta model, Samriddhi model, and then duplex model. This Samriddhi model and duplex model, these two models are developed by us at IIT Guwahati. So you can see the difference here. In the anaerobic digestions, we have done some modification inside the digesters. Okay, so this was done before finalizing the dimensions. We have done a lot of numerical studies, and then finally we have found out the optimum height required for maximum conversion of this biomass to energy. Okay. And also we have developed one another kind of digester called duplex model. The purpose of development of this duplex model was to break the scum formed in the inside the digester. Actually, what happened in fixed dome type digesters? So as you know the principle, like if you feed something here, then once this micro will start working, then what will happen? Gas generation will start. Okay. Then what will happen? This part, actually, normally this is something like 33% of the total volume. Okay, is occupied by this gas. So it will give some kind of pressure. When it apply pressure, what will happen? This slurry will come out. Okay. And then once we collect it, then again level will rise. So that will work in displacement mode. But what happens with times here? This there's a membrane, okay, which separates this gas and liquid and solid. This may be two-phase mixture because it's like a slurry. So it forms some kind of solid membrane. Okay. So what happens? Sometimes this gas generated here, this cannot come out because of this very thick membrane which is formed. So what this gas will do, then gas will come out through these holes and it will be lost. Okay. So that's why it is recommended that we must have something which can break this scum. Okay. So scum breaker is required to break the scum. Okay. So to avoid this problem, what we did, we have two different dome, and then we have provided some kind of recirculation so that it breaks the scum themselves and we can get continuous generation of biogas. Okay. So these are these are a fixed dome type biogas plant, and this is actually floating drum type biogas plant. Okay. So in case of floating drums, this object will float. Okay. Based on the gas generation, it will go up if the gas generation is more. This goes down if there is no gas generation is lower, and if we collect the gas from the chamber. Okay. So these are the two basic differences here. Lot of moving components, but in case of fixed dome, there is no moving components. Okay. So let us learn the practical differences between these two type of biogas plant. Like cost is more in case of floating drum compared to fixed dome type, and corrosion is more because this structure, what I have shown here, this structure is metallic. Okay, this structure is metallic. So as you know, this biogas also produces some kind of sulfur. Then it reacts with this oxygen present and then moisture present there. Then it produces sulfur dioxide, and which is corrosive to these metal surfaces. So corrosion is more in case of floating drum type biogas plant compared to fixed dome, and maintenance is more in case of floating drum compared to fixed dome type digester, and thermal insulation is bad in case of floating drum type, and fixed dome type it is very good because it acts as an insulator, because bricks are used. Here metals are used because metals are good conductor of heat. Okay, that's why it is bad as far as conduction is or heat loss is concerned. And scum travels is less likely here, because what happens in this case, this can be rotated. This drum can be rotated. Okay, once you rotate the drum, then no scum formation will not be there. So minimum scum formation is be there. But in case of fixed dome type, it's more likely this scum formation is will be there. This gas production per unit volume is higher in case of floating drum compared to fixed dome type biogas plant. And as I say, this scum breaking is done by rotating the drum. But in case of fixed dome, we need to have some kind of external stirrer, something like we have developed some kind of buffel kind of things. You can have a hinge there, and you can pedal it, and then that will break the scum. So sometimes we need to do it so that we get the continuous flow of biogas generation. And it's a danger of gas, mixing with oxygen due to leakage and crack, which is less likely in case of floating drum, and for fixed drum it is more likely. And gas pressure is constant for floating drum, and it's variable for fixed dome type biogas plant. And for machinery workmanship, it is average skill is required, but in case of fixed dome, so skilled manpowers are required. So that's how MNRE produces some kind of certificate, that is renewable energy technicians. So they have to be trained for making this kind of structure, because it's a specialized hand is required for making this fixed dome type biogas plant. And it's repairing and repairing of gas holder is easy, and so for fixed dome it is difficult, because sometimes if that mason makes some mistakes at the time of construction, then it's a big mistake. So if we have to rectify it, then we have to do a lot of things. So for example, we have without testing something, we have fed this feedstock, and it's full of feedstock, and then you are feeding regularly, but the gas is not generated. Then what to do? You have to clean it again, and we have to check whether things are properly designed or not. So for that, it is not something like just clean it and someone will enter there and do the rectification. So because that the chamber might have filled with methane gas. So once you enter, then oxygen will be not there. Then only methane will be there. So under that condition, no one can survive under that condition. So first, we need to check. Maybe one chicken may be allowed to enter. If chicken is alive, then it is confirmed that oxygen is there. Then people can come and do the rectification. So it's a difficult thing for maintenance. And soil of feed material can be procured, processed dung and natural slurry, and other material along with slurry can be done for fixed dome type biogas plant. Now we'll describe the anaerobic digestion process. So you can see the processes, then microorganisms involved, and then kind of material used in the anaerobic digestion process. So if we look into this material, so we can have maybe carbohydrate, protein, then lipid. Okay, so all the things can be fed together, and then that will be converted to amino acids and sugars by using cellulolytic, lipolytic, and the proteolytic microorganisms, and that process is known as hydrolysis. And then these amino acids and sugars are converted to fatty acid by with the help of fermentive microorganisms, and the process is known as fermentation and or acidogenesis. Okay, and then this acid, fatty acid, may be converted to acetate and hydrogen with the help of hydrogen-producing microorganisms, and the process is known as fermentation acetogenesis. And finally, our target is to generate methane with the help of methanogenic microorganisms, which convert acetate and hydrogen to methane. Okay, and that process is known as methanogenesis, right? So this process, we must know, and this will help us what is happening inside the biogas plant. And in order to strengthen the life of the microorganisms, what are the things to be controlled, that we must know. Once we know this process, from that we can think of what could be the appropriate environment for growing those microorganisms. Okay, and also we must know the chemical reactions involved in anaerobic digestion. Okay, so here this glucose is converted to acetic acid, okay, in presence of H2O, and we'll get 4 mole of hydrogen, and then we'll have acetate and then carbon dioxide. Then acetic acid is again converted to methane and carbon dioxide, and also we have ethanol, which is converted to methane plus acetic acid. Okay, and finally this carbon dioxide, what is generated in the acetic acid conversion, and then hydrogen in the glucose conversion, which actually finally leads to methane formation. Okay, and then water vapor, right? So if we talk about the overall conversion reactions, it goes something like this: C6H12O6, which presents in that feedstock, which is converted to 3 mole of methane and then 2 moles of carbon dioxide. This is something like the overall what is called chemical reaction. Okay, so now let us discuss something, how efficient these reactions are at the microbial level. But no, when we talk about system level, the efficiency decreases significantly. So this energy efficiency of conversion of carbohydrate to methane in the AD plant can be visualize by considering this aspect. Like molecular weight and heat of combustion of glucose is about 180 and 16 megajoule per kg. So the molecular weight and heat of combustion of methane is about 16 and 55 megajoule per kg. So referring to this overall chemical reactions, that 180 kg of this glucose converted to 48 kg of methane. Okay. So if we talk about energy stored in 180 kg of glucose is equal to 180 multiplied by 16 megajoule per kg. So what we will get? 2880 megajoule. And then energy stored in 48 kg of methane will be about 55 multiplied by, we have 48 because there are 3 atoms, so 16 multiplied by 3, it will be 48. So it will be 2640, right? It will be megajoule. That means if we are defining this conversion efficiency, which is nothing but this much of methane we get out of this much of glucose. So this is 1640 by 2880, which is equal to 92%. You see, the conversion efficiency from glucose to methane is about 92%. Okay, so it is very highly, or say we should say highly efficient conversion process. But when we talked about system level, its efficiency decreases significantly. So we must know these properties of biogas. What is the density if 40% carbon dioxide is present? If we remove the carbon dioxide, what is the calorific value of biogas? Okay. So with carbon dioxide or 40% carbon dioxide, it is 22.35 to 24 megajoule per cubic meter. And if we remove the carbon dioxide, then its value increases up to a value of about 36 megajoule per cubic meter, which is very good fuel value. And octane rating with 40% carbon dioxide is 110, and without carbon dioxide is about 130. Okay. And air to methane ratio by volume for complete combustion is 10:1. Okay. So biogas production and its application, if we say, like and its composition, sorry, like fat, then protein and carbohydrate. So these many elements should be there in the feedstock. And then if we talk about biogas production, it's about 1200 liters per kg of dry substrate for fat, and protein is about 700 liters per kg of dry substrate, and for carbohydrate it is 800 liters per kg of dry substrate. Okay. And then methane is about 67 in case of fat, then protein is 70%, and carbohydrate is 50%. And carbon dioxide generation can be seen here. So for carbohydrate, carbon dioxide generation will be high, followed by protein and fat and protein. Okay. Now, also we must have some idea about biogas and its equivalent energy. Say 1 cubic meter of biogas equivalents to how much of diesel? So if we have to equalize it, then we can say it is about 0.52 liters of diesel, then 0.62 liters of kerosene oil, 3.5 kg of wood, 12.3 kg of cow dung, cake, 1.46 kg of charcoal, then 0.43 kg of LPG, 1.6 kg of coal, then 0.47 kilowatt of electricity. Okay, so these are something like to visualize qualitatively how good the biogas is. Okay, and then how equivalent energy can be generated, and what are different factors which influences the production of biogas yield. These factors are very essential to maintain at an optimum rate. Okay, like carbon nitrogen ratio. So if we have to use a mixed of feedstock, then we have to find out what is the mixed carbon nitrogen ratio. Okay, so for example, if we are planning for utilizing, say, kettle dung, so its carbon nitrogen ratio is about 25 to 30, which is actually optimum range of CN ratio, which is to be maintained for higher biogas production rate. Okay, so that's why this kettle tanks are without condition we can use it in our anaerobic digestion. And temperature, when you talk about temperature, there are three categories of temperatures. Maybe cyclophilic if our working temperature is 25 or below, and mesophilic if it ranges from 35 to 40, and then thermophilic if it ranges from 50 to 65 degrees C. Okay, so based on the situation or based on the requirement, we can select the appropriate range and we can do the anaerobic digestion. So sometimes thermophilics are also important, because if you need more biogas at short duration, then we will go for this. And otherwise, if we can maintain this mesophilic temperature without investing so much of energy for heating, then mesophilic temperature range is perfect. And also pH value we need to regulate, say about 6.25 to 7.5. Okay, so there are many studies based on that. No, we can investigate how this can be optimized, the CN ratio, and only under the condition like pH value, if it ranges from 6.25 to 7.5, we will get the maximum biogas production rate. Loading rate is also important, which defines like amount of waste material fed per unit volume of digester capacity. Then hydraulic retention time, as I have defined at the very beginning slides, this is nothing but the average period that a given quantity of input material remains in the digester to be acted upon by the methogens. Toxicity also very, very important, because say we cannot give some kind of substances which is not good for the microbials growth, something like soaps. So we cannot or we should not allow the person to give soaps or this kind of material to this biogas plant, because this will inhibit the growth of pathogens or microbes. Then dilution and the consistency of input, like the amount of total solid to be considered, that has to be constant, and volatile solid to be maintained about 75. Otherwise, if it is very, very dilute, then what will happen? This microbial activity will be not proper and the solution will be acidic. Okay, so again, if it is very, very high, then again it will be difficult to have microorganisms activity and biogas production, subsequent biogas production rate. And the effect of agitation on biogas yield also important, because as I said, this come from breaker is also required for enhancing the microbial activity, and the effect of additives are also important on biogas production rate. So now we'll present some of the numerical values of the feedstock which carries this CN ratio. Like cow dung, CN ratio is about 25, and then poultry droppings, it is 5.2. You can see the values for different substrates. You can see for raw sawdust is 511, so it's very high. We cannot use this sawdust for anaerobic digestion straight away. We need to do something before it introduced in the anaerobic digestion. So we need to do some kind of mixing. Okay, and we'll have retention time for various feedstocks if we maintain at 35 degrees C. Like cow dung, it's about 50, poultry droppings 20, then rice straw 33, then sugarcane tops is 43, then water hygiene about 46 days. Also, we must know some kind of design information. Say, if we are interested about volume of the digester, we must know the quantity of cow dung to be added, and then quantity of water to be added, and then density of the slurry, and H is nothing but hydraulic retention time. Okay, so that way we can calculate what is the V1. Okay, so V1 is nothing but volume of the digester. If we consider 40 days hydraulic retention time, it's about 1.81 cubic meter, and this digester volume should be at least view 1, but there are presence of bubbles of gas in the digester. So increase volume will be about 10% of that volume V1. Okay, that's how it is. Total volume of the digester will be V1 plus 0.1 multiplied by V1. So it will be about 2 cubic meter. Okay, for this condition. And if we talk about size of gas holder for family size biogas plant like KVAC and Jonta model, 50% of the capacity of the biogas plants are now occupied by the gas holders. And for Dinbondu model, about 33% of the size of the biogas is nothing but gas holder. Okay, and for community size or institutional biogas plant, the size of the gas holder is about 50 to 70% of the size of the total biogas plant. Okay, so these are some of the sizes normally used in most of the installations. And also we'll show some of the slides about different studies what we have carried out, like how we have developed the methodology for making one improved biogas plant. First, what we did is a bench scale studies. So we have this kind of digester, and then this is inverted cylinder, and it is immersed under water. So this is thermocouple, and one pipe is for connecting to this measuring cylinder, because gas generated here in this digester will come through this pipeline and it will occupy here, and it will slowly press it. Water displacement will be there, and by reading this graduated cylinder, we can know the amount of biogas production. Okay, and then what we did, we have done two different digesters, and it is interconnected before it's collected, before gas is collected from the second one. Okay, this is digester 1, digester 2, and this is the interconnection, and temperatures are measured continuously, and then we have collected the gas generation. Okay, so advantage is like it breaks the scum, and then we can have we can meet the more demand of biogas generation. So also we have done some kind of numerical studies to strengthen our understanding and to optimize the height of the walls, which is required inside the biogas plant for maximization of biogas production rate. So these studies were implemented in the field digester, and we have done the analysis for 2 years, and after that we have established that our findings were quite effective, and we have installed that improved model in some of the places nearby AICTE, and they are so happy that they want more number of installations, but because of this fund crisis we cannot give more installations, but these were very success stories. And these are some of the investigations of biogas production in laboratory scales. So we have done some work on cow dung and some work on vegetable waste, and also some work on co-digestion. So what you can see here, digester ABCD stands for biogas when biogas generation when only cow dungs were used, and this EFGH what is seen here, this is for vegetable waste. Okay, and so we have done some total solid content and cumulative gas production. So you can see this cumulative gas production is lower in case of vegetable waste compared to cow dung digesters. Okay, so we can also see the pH variation and temperature variation. And this figure shows how we have done the calculation for lab scale studies. And also we have one unit at AICTE. What we have done there, so as you know, there is a issue of gas production in winter. So when temperature goes down, so these microorganisms they suffer in thermal stress, and they could not perform well. So what happens, we have used one configuration like PVRS, and this was used to run the DC pump, and this water is circulated through this evaporative tube collector, and then water is circulated in a heat exchanger, which is placed at the bottom of this biogas plant. Okay, so what you can see here, these are the thermocouple. These are part of this stirrer, and thermocouples are there throughout. Okay, so these are connected here in the data acquisition system. Okay, and pictorial view can be seen here, and we have this biogas balloon, and that can be transferred to internal combustion engine. So this is part of SERB project. So this part was there, and then the purpose of this part is to generate biogas at certain conditions, and that will feed to the IC engine. And again, we have one gasifier, and then we see which one is replacing what, and then what is the combustion efficiency. All the engine performance and emission characteristics we studied under different combinations of biogas and producer gas mixture. So this kind of heat exchanger we have designed. Okay, so design parameters are here. So this will install here at the bottom, so that we can maintain the temperature of 35 degrees C. Okay, which is in measurable temperature range. So pictorial view can be seen here, number of turns and all. These are well designed. And also in field biogas plant, we can see the temperature variation and gas production. So you can see the temperature position, and we can see this temperature variations with and without heat exchanger. So this part was without a heat exchanger, and you can see that with the heat exchanger that variations are very, very minimum. So that indicates that we will be able to achieve this temperature control, and we can get the higher biogas production rate under that condition. So it shows the temperature coordinates. So these are connected to the data acquisition system. Okay, and you can see this is a part of the scum breaker. Okay, which is introduced in the biogas plant. Okay, and this is weekly biogas production, and this shows the variation of temperature. And also you can see here it's a existing Dinbandhu model, and improved model is something like this. So existing Dinbandhu model, you cannot see this kind of walls, but in case of improved model, which is known as Samriddhi model, we have some kind of optimized walls inside the biogas plant. So you can see here we have also compared the performance of biogas plants. So when these biogas plants were installed, the underground and above ground. Okay, so which one is giving the best performance? So it is found that when we install the biogas plant over ground, and this part is exposed to the sun, then what will happen? More thermal stress will be generated, and because of that, gas production will be very, very low. So we need to maintain some kind of height from the ground, which is known as radiation penetration depth. So if we maintain it, then we are expected to get higher biogas production. So this is what we can see here is a duplex model, and schematics are shown here. Okay, so this is the our inlet tank, and this is the pipe through which slurry introduced in the register 1. Okay, and then these walls are fixed here, and then it goes to this next wall, next chamber for complete digestion. Okay, so gas produced here will be collected here, and also we have one recirculation loop. So gas produced here, it goes here, and again gas produced here will come here, and then finally we will collect the gas from here. Okay, so we have done a lot of studies, and it is found that digesters with recirculation will give higher biogas production rate. And also we can classify these biogas plants like based on their relative size, function, location. So these classifications are something like family scale biogas plant. It's a very small scale and up to 6 cubic meter per day. And farm scale biogas plants are up to 15 cubic meter per day. And centralized biogas plants like medium to large scale is more than 15 cubic meter per day. Okay, these are some of the classifications. And the family size biogas plants are something like this. Figure A shows the Chinese type, and figure B shows the Indian type. Okay, so it has got modified to a different shapes. So this was something like that. We have our slurry inlet, then we'll have anaerobic digestion, then effluent chamber, and gas collection will be there. So this is gas collection, then inlet, then an anaerobic digestion reactor, and then we'll have effluent chamber. And farm scale biogas plants look something like this. Okay, so here we have what is called digester. This is digester tank. Okay, and then we have biogas storage tank, and then we have combined heat and power plant. Okay, so these kind of plants are in most of the Western countries because they need both heat and electricity. So that's how they are having this kind of technology. Okay, and this kind of technology are also available. So here basic purpose is same, but size is very big, and at the same time storage facilities are there. Okay, and let us take a centralized coordination plant. How actually it will look, and then how difficult it will be, and how it will work. Okay, so this is the basic purpose of introducing these slides. Like we can collect this animal manure. It may be cattle, any cattle, then pig, then poultry manure, and then maybe biomass suppliers like industrial organic waste, MSW. Of course, this will be organic, and sewage sludge that has to be transported to this unit, and then it goes to this transportation system, and then we will be having centralized biogas plant where homogenization will be done, then digestion will be done, then reduction of odor and nuisance will be done, and then product quality will be checked. Okay, and once this gas is generated, then that can be used for heating or power generation. Okay, and also we can compare this amount of carbon dioxide reduction and reduction in air pollution, then effective energy utilization. So these are something like we can show them by utilizing this waste, what kind of wealth we are making. Then we can have a separate separation of digested biomass, and that can be used as fertilizer for maybe agricultural field, or maybe vegetable gardens, or any other applications. And that can be transported and storage facilities out of the shed. Okay, so that can be done. So this will work in a centralized system, and these are the things it is included. So cyclically also we can show, like we have anaerobic digestion, and then we have crop farming. From that, animal farming will be there. Animal extractor can be used in anaerobic digestion, and then food industries. Then the crop will be used in food industries as well, like alcohol making. And from that also we can have biogenic waste, and that can be used in anaerobic digestion. And then we can distillate it digest it for fertilizer. So that way, it will work in a loop, and it will be a more sustainable process for energy generation as well as its byproduct utilization. So there are some rules for sizing biogas plants, like 1 kg of dry kettle dung produces about 1 kg of 1 cubic meter of biogas. Then 1 kg of fresh kettle dung contains about 8% dry biodegradable mass. Then 1 kg of fresh kettle dung has a volume of about 0.9 liters. Then 1 kg of fresh kettle dung requires an equivalent volume of water for preparing slurry. Then typical hydraulic retention time maybe varied from 40 to 55 days. So if we take this problem, then see what happens. So this problem goes something like this. An engine generator system running on biogas is proposed to be installed at NIT Arunachal Pradesh, maybe, to produce 2 kilowatt of electric power. Then we need to estimate the volume of digester of the biogas plant required. Okay, so calorific value of biogas is about 20,000 kg per cubic meter. Then efficiency of generator is 90%, and engine efficiency is 30%, and hydraulic retention time is 40 days. So we can make this kind of block diagram. So biogas plant, then engine, generator, and electric power. Okay, so electric power generation is 2 kilowatt. Then input here, if we write input power of the generator, it will be this output divided by generator efficiency. So which is nothing but 2.22. So this will be about 2.22 kilowatt, right? So again, engine efficiency is given as 30%. So engine input we can find out. So this divided by 0.3, what we will get is the engine efficiency, right? So which is about 7.4 kilowatt. And then this biogas, this energy is something like the amount of biogas energy, right? Then from that we can calculate what is the MF into CV of that feedstock, which is equal to power input to the engine. Then from that we can calculate the MF required and all. So this power input to the engine is here. It will be 7.4 divided by 0.9 divided by 0.3, because generator efficiency is 90%. So we can get 7.4 here. What is shown here, 7.4. And then quantity of biogas required is 7.4 divided by 20,000, which is about 0.00037 cubic meter per second. And then for continuous operation, biogas required will be about 31.96 cubic meter per day, because it will be in 24 hours and it was in second, so it will be multiplied by 3600 and then 24 hours. Okay, that's why it is in daily. Then dry cow dung required is about 31.96, because we have to use that methodology for designing, what already I have shared in the last slide. Mass of fresh cow dung required can be calculated, which is about 400 kg per day. And then volume of slurry of cow dung required is about 559.6 liter per day. And also we have to add the similar amount of water, and that's how this volume of slurry will be about 719 liter per day. And if we consider hydraulic retention time 40 days, then we can calculate the digester volume will be about 28768 liters, which is equal to 29 cubic meter. Okay, so in order to generate 2 kilowatt of power, then we need to have a volume of 29 cubic meter. Okay, so that big volume is required to fabricate it. Okay. So now let us take a quick study on byproduct of biogas. It's a slurry, good organic fertilizer, and you can see these values of C and P, CN ratio of this fertilizer, and other content, nitrogen, then phosphorus pentoxide, then other elements presence. So we can upgrade this organic fertilizer, what we normally generate from anaerobic digestion, and that process is known as vermicomposting. Okay, so in vermicomposting we'll have 3 compartments, like pre-composting, compost pit, and then vermicompost pit. So in vermicomposting process, in the pre-composting process, which takes about 15 days, and composting process takes about 30 days, and vermicomposting takes about 45 days. So you can see their configurations and then how it works, like cow dung, slurry, biodegradable waste, and then grass. These are placed in the pre-compost pit. And then in case of compost pit, we'll have this kind of segregation, like first dry grass and plantation trees will be there, then followed by cow dung slurry, then water hyacinth, then cow dung slurry, then dry cow dung and vegetable waste. So that way we have to make, and then we have designated or defined height to be maintained, okay, for doing so. And for vermicompost, you can see it is starting from pebbles, sand, soils, then vermicompost with worms, then grass molas. Okay, so you can see the height required, 1 inch, then half inch, then 4 inch, then 1.5 inch, then half inch. So that way we have to make the pit, and once it is ready, then we can release the vermicompost, and we can get compost from 90 days onwards. So after it is started, then continuously you can get the vermicompost. Okay. So how to prepare this? First, you need to make one shed for a small capacity. This 25 by 12 by 8 and then 3 concrete tanks of size 3 inch wide, 1.5 inch height, and then a variable length for pre-composting, then composting and vermicomposting. So you can see the processes. This guy is very busy in chopping the banana tree. Okay, and then they need to keep in the first pit for about 7 to 10 days. Then we need to sprinkle some kind of slurry or cow dung with water to facilitate decomposition. Then pre-composted the material are then transferred to the composting tank in layers. Okay? Then the water need to be sprinkled to keep the moisture level at 60 to 80%. And after 20 to 25 days, this composted material are to be transferred to the vermicompost pit, and where now we need to release the worm for their activity. Okay. So after putting the earthworm, it is to be covered with dry hay and regulated the amount of water need to be sprinkled. So this is very, very important because moisture need to be maintained. So vermicompost will be ready for harvest after 30 days. Okay. So that's how it works, and is now harvesting and is screening, and packaging will be done, and the labeling can be done based on the farm size and farm name. However, precautions need to be considered, like it need to be protected from direct sunlight, and need to be maintained moisture content of 60 to 80%, and need to protect from ants, rats, and birds, because these vermis, once they saw, they will take it as a food. And need to maintain carbon nitrogen ratio about 30:1, and temperature should be within 12 to 29 degrees C. And pH to be maintained about neutral, close to neutral. It's may vary from plus minus 5. It's fine from the neutral. And for large vermicompost projects, so for example, for processing of 125 to 150 tons of organic waste per month to yield about 50 to 55 tons of dry vermicompost, 1,000 kg of or earthworm earthworms are required. Okay, so this thumb rule might be useful sometimes for you all for making a large vermicompost unit. So the work can be initiated with 7 lakhs of earthworm that work on organic waste. Okay, so this data was taken from Director of Bioecology, KVAC, Mumbai. And also, I'd like to share one case study, like how this biogas solar thermal hybrid system can be sustainable process for dairy farm. So major components of the systems are biogas plant to be operated with an input of 300 kg cow dung daily, and one 5 HP diesel engine is required. Initially, it starts with 100% diesel fuel, and subsequently, engine switch to dual fuel mode with fuel ratio of 80% biogas and 20% diesel. Okay. One flat plate collector is installed on the roof of the building for the supply of hot water, for cleaning of cans and milk sealing equipment parts. Then an insulating tank stores this hot water, and which is mounted on the top of the building. And biogas is generated in KVAC type 14 dome, capacity 12 cubic meter per day gas production, and biogas from the plant is taken to the milk sealing center through the GI pipe. Okay, you can see the configurations how it works. So this is something like this. This is the insulated tank where water is stored, and this is the flat plate collector. And then you can see this is the biogas is no supplied to this dual fuel engine, and then other components are run. Okay, so here we have this paper compression refrigeration system, so we can refrigerate it and we can make the system happen. So with the successful commissioning of this plant, the milk cooperation society has become economically viable, and milk production farmers, producing farmers of the area are earning well. Okay, that's the message they would like to give in the paper. So we can also compare the economics of family-sized biogas plant. If we consider size of the biogas plant is 6 cubic meter. So we can compare KVAC Jonta and then the model, and we can consider the initial investment of the plant, like cost of civil construction, cost of gas holder, cost of gas pipes and applications. Then we may be operating costs for the plant, and an annual income from the biogas plant. Okay, and under that annual income from the biogas plant, we can have income from the biogas in terms of LPG and income from manure. If you compare, then what will happen? Profitability and the percent return on investment also you can calculate. So this is the payback period, which is 6.25, then 3.75 for Zonta, and then 3 years for the mono model. Okay, so that way we can do the entire calculation. And also we can study some kind of social aspects of biogas plants, like individual level. Then efficient utilization of waste can be done by employing this kind of biogas technology. Also, we can improve the cooking and lighting, and efficient utilization of time. Then improve the sanitization. Then fuel for energy, fuel for engine for pumping and other purposes depending on the gas supply, and feed for animal and fish culture. And national level, we can provide energy, or we can reduce the energy imports, and uplift of social and economic life in rural areas. Okay, that means energy security you can do. And in community level, we can reduce pollution, then increase production, productive employment, and increase scope for small scale industries. So these are some of the things we can extend our list for different levels. And there are some challenges, like cleaning of biogas is a challenge. So if we can develop a proper cleaning methodology, then really we can augment the calorific value of biogas plant to a very high values, something like close to 39 megajoule per cubic meter. And we need some kind of compression system. If we use say what is called fixed dome type biogas plant. So because when we use gas, slowly its pressure is decreases. So in between you need a chamber which can give constant pressure to the system. And storage of biogas and bottling is also important. Okay, so there is scope of doing a lot of research, especially in those areas what I mentioned. Now let us summarize what we have discussed in this presentation. We have demonstrated how anaerobic digestion technology is helpful for rural development in sustainable way. And biogas produced is a green replacement of unprecedented fuel, like fuel wood, dung cakes, and crop residues, etc. And this biogas technology has the potential to meet the energy requirement in rural areas, and also counter the effects of reckless burning of biomass resources. Okay, so as you can see here, so we can have this livestock waste, then crops, we have wastewater, then food waste. So all these things can be fed in an anaerobic digester, and we can generate biogas and digest it. So once we have biogas, this biogas can be utilized for maybe heating purposes, or maybe cooling purposes, or maybe cooking purposes. Or this biogas can also be used directly for electricity generation by using this engine route. And we have we can use this as a vehicular fuel. And these digesters, we can enrich the quality of this fertilizer. And fertilizer, as a fertilizer, we can use it, and also we can enrich the quality of this fertilizer. And also livestock breeding can be, one of the applications. Okay, so I can see the applications. This is for cooking, lighting, and then for vehicular fuel. There are some countries already they are in the process of utilizing this biogas as a vehicular fuel, like in Sweden. And being relatively clean cooking fuel, biogas reduces the health risk associated with a conventional solars. Okay, that's how it is so important, because in the rural places you can see a lot of solars having very low efficiencies of conversion. So you can see only smokes, lesser amount of flame. So if you can give this kind of improved technology to those people, then hopefully their quality of living will be improved, and they can minimize a lot of health issues associated with it. Okay, so thank you very much for your attention. So let me know how do you see the prospects of biogas technology in your place, so we can always discuss. So if you have any questions, we can discuss now.
Good afternoon, sir. Hello, sir. I am audible.
Yes, yes.
Okay, sir. So myself, Dr. Devarshi Malik from GIMT Guwahati.
Okay.
So I want to ask you one question, sir, regarding the fixed dome plant, that is the Dinabundu plant you have described earlier. Sir, the mesophilic temperature range is around 20 to 40 degrees Celsius. So in the winter season, the temperature is fall down. So in this case, the gas production rate is decrease, or we have to take some preventive measure.
Yeah. Yeah, well, the gas production will reduce, and because of that, we have what we have shown. You can have different methodologies. Say what we are trying to do here at our center. We have an heat exchanger. Okay, we have designed a heat exchanger which is installed in the what is called biogas plant, and then we try to regulate the temperature by utilizing the solar energy. At the same time, since we have already designed one more biogas plant called Dinmondu, not Dinmondu, it's called Samriddhi. So there, if you know, we have installed walls inside the biogas plant. So that the walls were so designed that we'll get uniformity of temperature. So that was a very interesting observation we got out of the MNRE project, what we got a long time back.
Okay, thank you, sir. Actually, we have to spend some, but the extra cost should be involved in the winter season, right, sir?
Yes, yes, yes. But no, see, how precisely you are designing your biogas plant. That is important first. Suppose if you are designing the biogas plant for say pipeline supply. Say as I said in GAIL, Gas Authority of India Limited, they have ambitious projects like if you are generating some kind of purified gas that can be injected in the pipeline of natural gas. Okay, so that way, if you are doing very precise plan, under the condition, of course, you need to spend some money on enhancing the quality as well as the maintaining the temperature. But if you are talking about family change biogas plant, then I think the one we have developed, that is a Samriddhi model, is fine. So that can be suggested, because already we have installed that biogas plant in many of the places, and people are so happy about with the performance. In winter also they are not facing so much of problem. Of course, there is a reduction in biogas production, but they are not stopping. Okay, biogas they are getting. So that's the difference between our Samriddhi model and then the one which is conventionally used.
Yeah. Thank you, sir.
Welcome, Dorsey.
Am I audible?
Yes.
Good afternoon, sir.
Good
Sir,
afternoon.
my question is, we can make government should make some plans that biogas plant is compulsory in a compound or in 2 or 3 houses. Then there is more possibility that we can save our energy, as well as we can contribute to renewable sources of energy.
Yeah, true. Your observation is really appreciable. Yeah, that government should initiate. And what information I should share based on your disquiries? Like government has already given a lot of money to forest department. So they are actually responsible for installation of family size biogas plant in rural places. So every year they spend huge amount of money in installing this fixed dome, primarily fixed dome type biogas plant in many of the states of the country. But no, this initiation and then utilization should come from our own mind. Say, in my household, I must think that way. So that way we should be motivated to utilize this waste for energy generation.
Yes, sir. Thank you, sir. And sir, again one question is, like in Arunachal Pradesh, we can't make biogas. I have read in some news or in article that we can't make biogas in hilly areas because the rate of degradation of microorganism is quite less.
No, this is not the case. This is not the case. I think what you said, I cannot accept it because, see, what do you need? You need to construct that system, right? If it is a fixed dome, then we have to make some kind of FRP and all, and then we need to provide this slurry like water and then kettle down mixed. So if you are making that no down as a lower part properly, so that no heat is heat loss is taking place at the same time, no leakage is there, then I think it will work perfectly. Because in near to this Itanagar, this temperature is very good for biogas generation because it goes up to 40 and all. So at 35, 40 is a very good temperature. Okay, so it will work perfectly.
Okay, sir. Thank you, sir.
Okay.
Any
Sir,
question from
yes.
anyone?
Yeah, this is from Emmanuel. Am I audible, sir?
Yes, yes, you're audible.
Sir, actually, it's my small doubt. Actually, you have multiple inputs, sir. Actually, cow dung or any animal waste and agricultural waste or something. But by designing a digester, each one will have its own retention time. So before that, it must be processed so that it would match any other base like cow dung or something. So that to be done before deciding digester. Is it right, sir?
Yeah, correct. So these feedstock need to be characterized first. What kind of
Pre-processed.
feedstocks? Yeah, what kind of feedstocks you are going to utilize?
Yeah.
In your place. First, you survey the kind of feedstocks available there.
Yeah.
Then you can do the analysis. Like ultimately what I shown there in the energy conversion. Like when you say glucose, okay. So
Yes.
glucose is converted to 1 mole of glucose is converted to 3 mole of methane and then 2 mole of carbon dioxide. So from that we can do the analysis. The chemical conversion has to be more than 90%. So as I have shown, it's 92%. So even though this chemical conversion is 92%, but no system level efficiency is not that much.
Okay.
Okay. So we have to go step by step, and that's why in the very beginning slide I have shown these three categories. Like you have inlet tank, then fermentation, then outlet. And inlet is associated with your feedstocks, and outlet is the microbial activity and temperature, HRT, and other things. And then outlet is for we have fertilizer and all.
Okay.
So by considering this, we can meticulously do the calculation and we can have a perfect design for a particular location.
Okay. Thank you. Yes.
Anybody else?
Good afternoon. Welda.
Oh, good afternoon.
Hello, I'm Mr. Chaudhary from Assam Engineering College.
Yeah, I got it.
Okay, it's a very nice presentation. Yes, I have got a small query.
Yeah, please.
Now, if we can use the cattle dung with the kitchen waste,
Hmm.
so I think that can produce the more comparatively the more the biogas, na comparatively if we singly use the cow dung, na.
Huh. So what happened actually? We have tested cow dung and then vegetable waste separately and then mixed it. So all the three analysis we have done, but from the analysis it is found that no cow dung is superior always. So individually it is very difficult to actually harvest methane from kitchen waste. So we need to have some kind of other material which has to be mixed well before introducing to the anaerobic digestion for higher gas production, because it's acidic, it becomes very acidic. So we need to maintain those parameters, what I said, like pH value, CN ratio and all.
Okay. Depending upon the different kitchen waste, your the characteristics of the biogas will be also different, no, sir?
Yes. Actually, see, what kind of kitchen waste we are talking about? We are kitchen waste means sometimes whatever cooked and uncooked. So if it is uncooked like vegetable waste, and it is cooked, then it will contain some kind of oil. Then we have to remove the oil before we feed it to the biogas plant. So that way we have to decide.
Okay. Thank you.
Yeah. Welcome. So any other questions?
Anybody else? Devashish? No question from your side?
Hello, sir.
Okay.
Hello.
Yes, you are audible. You can speak.
Sir, in the fermentation process, we have to maintain an optimum temperature for maximum production of biogas. Yes, sir.
Correct.
So to maintain the temperature, we have if you use another source for temperature, then will it be beneficial for us?
Yeah, actually, part of your answer I already gave. That has to be decided how big your plant is. Okay, so at what application you are using it. So that way you can decide. So if it is a continuous operation, say for example you are running a hotel, then for that you need energy. So irrespective of days, you need energy. So that way you need to have this kind of arrangement because you need continuous energy. But if you are not so much of rely on this energy, then you can get you don't have to spend much money for making the arrangement for controlling the temperature. But no, of course, you can think of some new digester which can actually give approximately much what is called metabolic temperature range. What I mean to say when you install the biogas plant, so you need to consider some of the important things like radiation penetration depth and all. Okay, so that after certain depth you will get uniform temperature, but at the same time how are you going to utilize the solar energy for utilizing the how are you going to utilize the solar energy for heating the biogas plant? So there is a technology nowadays in Israel. They have developed some kind of sand bed. Okay, so digester is there, and then throughout that digester they have some kind of sand. So as you know, sand has got very good heat transfer capability. So heat capacity is more in case of sand. So they will store energy for a longer period of time. So that stored energy can be utilized for heating the biogas plant to maintain suitable temperature. So the amount of sand required to maintain the temperature need to be designed. So that way you can think of some new novel design to maintain the temperature.
Sir, for defined system, we have to maintain defined temperature, sir.
For different
Defined feedstock, we have to maintain defined temperature.
First, see, feedstocks are very sensitive to microbial health. So first you have to characterize, and you must know the parameters to be controlled. Say pH value, CN ratio, total solid content, temperature. Okay, so these will be fixed. These will be fixed because finally what happens? You are maintaining the growth of microorganisms, like primarily methanogenic microorganisms, right? So all the things these are same only, but feedstock needs to be prepared well, so that no, you cannot disrupt the functioning of the microorganisms what is present in the anaerobic digester.
Okay. Thank you.
Well, thank you, Dr. Pankaj Kalita. It was a very nice and informative presentation. And thank you once again for joining us and giving the expert lecture. Thank you so much.
Thank you, Manjula, for inviting me and delivering.
Most welcome.
Thank you very much. Yeah.
Hope next time also, whenever we'll have this kind of program, we'll have you as an expert. Thank you so much.
Thank you. Okay, then bye. See you.
Bye.
Thank you, sir.
Thank you.
So participants, in the next session will be from 2:30 to 4, and in that session we'll circulate the Google form for feedback and attendance. So all of you need to fill it up for today's session. Okay, so let's have lunch break till 2:30. So see you at 2:30. Okay, bye.
Okay.
Bye, ma'am.